We ended last week talking about acids and strong acids and weak acids, and so this section will be about bases. So strong bases, the definition is similar to a strong acid. A strong base dissociates completely in solution. Strong bases dissociate, they don't ionize because they are ionic compounds. So when you have a strong base, the hydroxide ion concentration is going to be equal to the concentration of the base. Just like with a strong acid, if you have 1 molar HCl, then you know that the hydronium ion concentration is 1 molar also. Most strong bases are group 1A or 2A metal hydroxides. And so here are some examples. This is not a list that you need to memorize like the strong acids. Any metal hydroxide that is soluble is going to be a strong base. So these are soluble things. They're going to separate into, this will separate into lithium hydroxide ions. So those group 1A metal hydroxides are very soluble, and so you can form concentrated base solutions with these. That's why we use sodium hydroxide a lot. The group 2 metal hydroxides are only slightly soluble. What's a little tricky about these is they produce 2 moles of hydroxide per mole of base. And there will be questions that try to trick you with this, okay? So strontium hydroxide, 1 mole of this produces 2 mole of hydroxide ions, okay? That's what this little 2 means here. So you do need to watch out for that. We don't use these a lot, but I'm sure there'll be a question on the next exam that's going to trick you and give you something like, strontium hydroxide and ask you what the molarity of the hydroxide ion is. And if you don't think about it, you'll just say, oh, well, it's equal to the number that you gave me, and no, it's that number times 2. So we talked about diprotic acids that they ionize in 1 step at a time. The bases don't do that. They dissociate just completely. They drop all their hydroxides. Any questions yet? Okay. Weak bases are pretty straightforward. Strong bases, so we'll talk more about weak bases. Weak bases are like weak acids. Most of the common weak bases produce hydroxide by accepting a proton from water. And so here we can use B as a generic symbol for a weak base, just like we used A for the acid. It's convenient because there's there is. There's boron. This is not boron, okay? This is just base, some weak base. So the weak base interacts with water and takes a proton from that, and that produces the hydroxide. The hydroxide was not part of the base to begin with, like in sodium hydroxide or something like that. So the most common weak base we run into is ammonia, NH3. So NH3 interacts with water. The water acts as an acid and donates a hydrogen to the ammonia. The base is accepting the proton, and we produce hydroxide ion. This is ammonium ion. This is the conjugate acid of this weak base. So when you have ammonium hydroxide or aqueous ammonia, those are 2 different ways of describing exactly the same solution. Okay, ammonium hydroxide is the same as aqueous ammonia. So like the acids, we have an ionization constant for the weak bases, and it tells us how strong they are. So here's our generic equation for the weak base. And so the Kb is going to be the products divided by the reactants, as usual. And again, water being a liquid doesn't show up in there because its concentration doesn't change. If the Kb is smaller, that means that the base is weaker. The small Kb means not many products are formed, so it doesn't dissociate or ionize very much. A large Kb means we've got a lot of this and it's a stronger base. Just like with Ka, we can define pKb as the negative log of Kb. Remember that P is just a function, the negative log of whatever comes after it. These are some common weak bases and their base ionization constants. This is not a list you need to memorize. There's nothing in here that you need to memorize. Notice with all of these, we've got whatever the base is plus water. The base accepts a hydrogen ion, and we end up with hydroxide ion. If you are given any of these formulas, you should be able to write out the ionization reaction. Okay? Any questions? So many weak bases are amines, and that's an organic chemistry term. A simple way of thinking about amines is they are ammonia with a hydrocarbon substitute for one of the hydrogens. So here we have ammonia. It's a nitrogen with 3 hydrogens. It's got a lone pair, and that lone pair is what can accept the hydrogen ion from water. In an amine, instead of having 3 hydrogens, 1 or more of those hydrogens is something else. So that something else is going to have carbons and hydrogens on it. Okay, so we took this H off and we plugged this on. This is called a methyl group. So you can kind of think of these as, like a building set where you can take off this piece and put a different piece on, right? With strong bases, the contribution of the autoionization of water is negligible. We don't need to think about that. So if we want to find the hydroxide ion concentration, the pH of a weak base is similar to finding the hydronium ion and pH of a weak acid solution. We're going to use the Kb instead of Ka. Again, we can generally neglect the contribution of the autoionization of water. We make an ice table, and we use the Kb expression to find the hydroxide ion concentration. So very similar to acids, but a little bit different. So we learn the pattern for acids, and then learning the bases should be just expanding on that idea. Okay, so let's find the hydroxide ion concentration and pH of a 0.010 molar barium hydroxide solution. So the first question is, strong base or weak base?
Weak base.
No. It's a strong base. So it's barium hydroxide. Any metal hydroxide is a strong base because it's just an ionic compound that dissolves. So that one's going to be a strong base. So pretty much any time you see OH in the formula, it's going to be a strong base. The ones that are weak bases are going to look more like these guys. You're going to look at that and you're going to think, how is that a base, right? Well, it's a relative of ammonia. Here we've got NH2. Ammonia is NH3. So one thing you do need to know is that ammonia is a weak base. Okay. So we have a strong base, and that means our calculations are going to be pretty simple. So if I have barium hydroxide, I can think about, well, what does that do when I put it in water? It dissolves, right? And it's going to form barium ions. And how many hydroxide ions? 2. That's the only thing tricky about this particular problem. There's 2 hydroxides. So you could think of finding this hydroxide ion concentration as being a stoichiometry problem, which, may or may not help. That might make it worse. If I have one of these, I get two of those. So if I have 0.010 moles per liter of this, I have twice that much, right? So this is one where you can definitely get away with just kind of thinking about it and writing down the answer. But I'm going to write out the whole thing because you may forget later. So that many moles per liter, that's what the capital M means. And we know either by looking at the chemical formula or by thinking about the chemical reaction here of it dissolving, there are 2 moles of hydroxide for every 1 mole of barium hydroxide. And our units cancel out and give us 0.020 molar hydroxide ion. Everybody okay with that? I had some questions over the weekend about the homework on the acids, and a couple of them were about things like HCl, and I can't find the Ka for it. How can I calculate this thing, right? Well, we can't find the Ka for it because it's a strong acid, and that means we can just calculate it very simply. So one of the tricky things is there are some very simple things that happen in this class mixed in with the more complicated things. And so sometimes it is that simple. So for this one, it was that simple. This is our hydroxide ion concentration. Okay, the next question though is, what's the pH? This is where we need to think about the circle of pH. pH and hydroxide ion concentration are on opposite sides. I'll just draw that out. With pH, and we have hydrogen ion concentration, and we have hydroxide ion concentration, and we have POH, and we have pH. That's the circle of pH. So I have this, and I want that. We can't jump across the middle. We need to go through hydrogen ion concentration or through POH. You can go either way. Choose whichever seems simpler to you. Okay? What seems simpler to me is to go this way. So I'm going to take my hydroxide ion concentration and I'm going to find the POH. So POH is the negative log of the hydroxide ion concentration, which is the negative log of 0.020. Negative log 0.020. So 1.69897. Normally I'd stop here with the 4 digits, but then, I wrote that and I'm like, oh shoot, I'd have to round up these guys. I'll just write one more and not have to round anything. So that's the POH. Do you remember what the relationship is between pH and POH? They add up to 14. Okay, so this is one of those that's just really simple. pH plus POH equals 14. That's because of logarithms. So if I have the POH, then the pH is going to equal 14 minus that. So 12.3010 And how should we round that? How many sig figs did this number have? 2. So we want our answer to have 2 significant figures. When we take the log of a number, remember the part before the decimal point is equivalent to the times 10 to the something in scientific notation. So all the significant digits are after the decimal point. So here I should keep 2 decimal places. 12.30. I think that's what the book is looking for. Is that a reasonable pH for a solution of a base? Yeah, we expect it to be above 7. If we come up with this as our pH, because we forgot kind of where we were, and we get 1.69, we should think, no, wait a minute. That's the pH of an acid. This is a base. I must have missed something. Any questions? It's Monday morning. Everyone's still partially asleep. It's okay. So am I. Okay. Let's do another one. Find the hydroxide and pH concentration. Hydroxide concentration and pH of 0.33 methylamine solution. And here's the KB. Is this a strong base? No. It's not something hydroxide, right? It's some other name. And the amine in here should be our clue that it's a base. Do we need to know the formula for the methylamine? No, we don't. We just need to know that it's a base. So we can write an equation, a chemical equation, describing how this ionizes without knowing what its chemical formula is, and we're just going to use B. B for base, not B for boron. So we put the base in water, and we get an equilibrium. The base takes a hydrogen ion from the water, which gives us hydroxide ion. So this is a generic equation for all weak bases. If you have the formula, you can put the formula here. You're going to tack an H plus on the end of it over here. It's all good. Any questions about that? So now we are going to make our ice table. And we can just use the chemical equation as the header row to organize things.
Are you able to hold the line to make it straight?
That's a good question. No, this app that I'm using is a little bit primitive. It's primitive and yet incredibly awesome. Unfortunately, the company went out of business 2 years ago. So at some point, they're going to update Windows and it's not going to work anymore. But until then, I am going to use it. So our ice table. Well, what's this 0.33? What's that the concentration of? It's the methylamine. That's the initial concentration that we're going to put into our ice table. So 0.33 is the concentration of our base. What's the concentration of water? We don't need the concentration of water, right? We don't even need that column in there, really. But if we just write this without the water, then we can't get to that part. So we have to write it in there, but it's not really part of the table. What's the initial concentration of BH plus? 0. What's the initial concentration of hydroxide ion? Approximately 0. It's 10 to the minus 7, which is really small. Okay, so now we can look at how do these things change? Well, the zeros can only go up. They're going to go up by x. Is this looking familiar? And this is going to go down by x. And then we add those rows. We add I and C to get E. We got 0.33 minus x. We have x and x. We can write an expression for Kb. That's going to equal BH plus times OH minus divided by B. So now we'll plug in the things that we know. Kb is 4.4 times 10 to the minus 4. And that's going to equal BH plus times OH minus. So x times x, x squared, divided by 0.33 minus x. Now what do? We solve for x. There's two ways we can solve for x here. We can try the x's small approximation, or we can use the solver. I'm going to just demonstrate x is small because that's more easily to demonstrate, and I want at least one of you to do the solver. So in the x is small approximation, we say, well, this is a small equilibrium constant, and so I'm going to say that this x being subtracted from 0.33 is just not even going to be missed. It's like the one peach falling off the truck, and so that's essentially 0. So then we can say that x is the square root of 4.4 times 10 to the minus 4 times 0.33. Okay, what did you get from the solver? Anybody? 0.1183. Okay. So, how can we tell if this one's okay to use? 5%? We need to see if this is less than 5% of what we subtracted it from. So if I take that and I divide by 0.33 multiplied by 100, that is 3.7%. So we could use that, right? We could also use this one. So this is from the solver, and this one's from x is small. Okay, so one of the questions is, what's the hydroxide ion concentration? Well, that is equal to x. So the first answer,
How come the numbers are
pardon me?
How come the numbers are off?
How come the numbers are off? Why are these a little different? Because this, we used an approximation. So when we go to round this, if I take this number, where's my pointer? If I take this number, and my hydroxide ion concentration should probably have two significant figures, right? Because that's what this is. I'm going to get 0.012 molar. If I use the number from the solver, what am I going to get? I'm going to get the same number, right? So even though these are different, given the significant figures, they are the same. And that's why X is small can work, is because if it's small enough, it doesn't really make a difference. It's a good question. If this ended up being a 1 here, if it didn't round up, that still would not be a big issue, because remember, there's always uncertainty in the last digit. So there's our first answer. Now we need pH. So I'm going to use this one. I guess I'll go with green again. I don't know. POH is the negative log . When I calculate POH, I don't want to use the rounded number. I want to use some extra digits. So POH is 1.9190. And again, I want to keep some extra digits. So pH is 14 minus that. .08098, 12.08. So I'm going to go over here and find out what the pH of this one is. Oops. Poor planning on my part. So I get 12.08 from using the X is small. I get 12.07 from using the solver. So if this was an exam question with multiple choice answers, you would see one of these as the correct choice. So if I put in 12.07 and you used the X is small approximation and you came up with 12.08, you should recognize that 12.08 is essentially the same as 12.07. The other things I would put in there would be like 1.92, because that's if you calculate POH instead of pH. Any questions?